A circular loop has the given radius and resistance values shown on the picture. At t equals 0, a magnetic field into the page is applied in the region where the loop is located. The magnetic field increases with time and it's proportional to the cube of time. The question is, what is the magnitude and direction of the induced current in the loop at the instant when B is equal to 1.7 Tesla? To find the magnitude of the induced current, let's apply Faraday's law. The magnitude of the induced EMF is equal to the magnitude or the absolute value of the time rate of change of the magnetic flux through the loop. Now, the EMF can be expressed as R times I following Ohm's law. R is the resistance of the loop, I is the induced current that we're looking for. And on the right hand side of our equation, we have d dt of B times A times cosine 0. B is the magnetic field, A is the area of the loop, that's the circular area, pi r squared, times cosine 0. The angle between the magnetic field vector and the area vector is 0, hence we have cosine 0, which is equal to 1. For the loop's area, we substitute pi r squared, and for the magnetic field, we substitute the function given in the problem, which is the only part that depends on time. So in the next line, let's take the derivative of the magnetic field with respect to time and rewrite our equation. The magnetic field function is proportional to t cubed, so when we take the derivative, we get a factor of 3t squared. And then we rearrange our equation to isolate I, the induced current. Now, before plugging in the numbers, we need to find the value of t, which is not given. So, but we are given a hint. We know that at that time, at that instant, the value of the magnetic field is equal to 1.7 Tesla. So let's use that information to calculate the value of t and then substitute all the numerical values to calculate the induced current. We rearrange the magnetic field function to isolate t and then substitute the values. The value for t is 1.7 Tesla. We divide it by the constant and take the cube root, and we get t equals 1.4 second. Now let's go back to our result for the induced current and calculate its numerical value. The result of the numerical calculation is 0.030 amps for the induced current. Now let's determine the direction of the induced current using Lenz's law. The magnetic field is pointing into the page and increasing, so the magnetic flux into the page is increasing. The response of the loop will be to oppose to this change. Because the flux is increasing, the loop will create a magnetic field in the opposite direction, and that's the direction of the induced magnetic field. So the induced field is pointing out of the page. Align your right thumb out of the page towards yourself and look at the direction of your fingers. Your fingers are curling in a counterclockwise direction, and that is the direction of the induced current. So the direction of the induced current in this loop, as the magnetic field into the page is increasing, is counterclockwise.